Okay, in this lecture, I'm going to continue talking about the surface integral. In the previous lecture, showing here, the link is given here. I talk about how to compute the parameterized version of the surface. And today I'm going to talk about how we're using the parameterized surface to compute the surface integral. Okay, so here's a recap of the surface integral. So the main idea of the surface integral is to compute the integration of some function, here say fxyz, over a surface and given by a sigma over here. So if you consider the fxyz as the amount of water collected per unit region at a point on the surface, and if you want to compute the accumulated water on the surface, so we can compute the surface integral over here. Now the key challenge to compute the surface integral here is I have d sigma, which means this is different from the typical dx dy because this little pieces on this surface, let's see here the d sigma is like very small tiny piece over here. This one can be harder written as dx dy. It's not equal to that. It's not equal to dx dz apparently because it's not. So that doesn't apply. So we sort of have to rewrite the surface integral in a way that we can solve. So as I mentioned last time, the main idea to solve the surface integral is to rewrite this one into a standard double integral, so we can compute the integration. Okay. All right. So today I'm going to talk about how to compute that. Okay, so last time we talked about the parameter representation of the surface and sigma. So if I give a point, so the main idea for the parametric representation is any point xyz, I can use just two parameters. Okay, assuming I have a 3D surface, I can two variables u and v. So any point on the surface, basically any point on the surface, I can use some u and some v to represent that point by plugging this function, the x of u and v, y is function of u and v, and z is function of u and v. And by figure out the lower bound, upper bound of u and v in a proper way, I can represent this surface in this way. Which means if I'm going to exhaust all the possible points for u and v, now by computing this x, y, z function of u and v, I can get every point here on the surface. So that's the parametric representation. Okay, now I'm going to talk about how to use it, okay, to compute the surface integral. Now, here's the main idea to compute the surface integral. If we have, here we assume we have a parametric representation of the sigma given this form. Now here I generally I give a general form. Typically we have u is this lower bound, upper bound, right? This is lower bound, upper bound. So let v have a constant lower bound, upper bound, so given by some numbers, and the inner side u is a function of this v. Okay, so the surface integral can be written as, so this is the original surface integral, can be written as a double integration over here. So we have du and dv. Now we know how that's just double integration. Now here's what change we make. So first of all, we don't use this one as my integral anymore. So we integrate only over an area. This is S. Well, this S is defined by u and v, the region of u and v. Okay, so this is a region we have. I'll talk about the next step, how to compute that. And the next step, we have to change this f function over here to replace this x, y, z by their parametric representation using u and v. Basically, I replace x by x of u sub v, y by y u sub v, and z is by z u sub v. Okay, replace that one. So my f function will become just a function of u and v. So this is just f u and v parameters. I don't have x, y, z anymore because x, y, z are represented by function of u and v. Okay, now this part is done. The next part is there's some actual term. It not just replace that. There's one actual term here is this is the norm, or this is inside here is just a vector. The vector is the cross product of two vectors. So this one is the partial derivative of r with respect to u, and the second one is partial of r with respect to v. So this r is just x, whatever function you have x, u sub v, y u sub v, z, you just replace over here. is what your parametric representation has. Then you do the partial derivative of this one with respect to u, cross product of the partial derivative of this r with respect to v. Now r is just, like I said, x, y, z, a function of u and v. Then you compute that cross product. Then next step, we compute the norm. Okay, because this is a vector, it's a 3D vector. So you sort of have something like this one, something here, something here, something here. This is what you computed. It's a cross product. The norm is just you do the square root of the first squared plus second squared plus third squared. That's squared. That's your norm. So this gives you also a function of u to v. Then you integrate that over u and v. Now we're done. So in more specifically, we can also write this one into, like I mentioned before, is you do the inner integration here. You can just split this one into two components. One is the inner integration over here. This is the inner integration over du. That's why this lower bound upper bound could be a function of the variable outside. Okay. Then you do the outside external integration. Okay. Now we're done. Okay. So at least we know how to compute that. Okay. So now I'm going to give you an example, show you how to compute this. This looks really complicated. I'll show you how to compute the surface integral. Okay. All right. So here I'm going to compute this example. Use this example. So in this example, I have a surface sigma, which is the surface of a half ball, the top of a half ball centered as origin with a radius of 1. So this is exactly the surface. The first example I mentioned in the previous lecture here. In this lecture, I talk about the first example is how to find a parametric representation for this surface. Okay. So I won't talk about how to do the parametric representation since it's already been discussed in the previous lecture. Okay, so and here also let f x y z, okay, function just equals to x squared plus y squared. So my goal is to compute the surface integral of f x y z over the surface. This is the surface we have. We're talking about the surface integral of this guy. Okay. Okay, there are a couple steps to compute the surface integral. So I'm going to talk about it one by one. Okay. Step 1 is the parametric representation of the surface. Okay. This one, as I mentioned, already given in the previous video. Okay, how to get a parametric representation of this specific surface. Okay. So I just pull this out from the previous slides. So the surface can be represented by cosine v, cosine u, cosine v, sine u, and sine v. Okay. If you don't know how to do this one, go back to the video to see how we get a parametric representation of this surface. And you sort of consider the first one. This is my x use of v. The second one is my y use of v, and this one is just z use of v. Okay. Of course, my r will just be cosine v, cosine. Just you stack them together. This is your r. Okay. Also, I have a lower bound, upper bound for u, and a lower bound, upper bound for v. Okay. Now we're done with the parametric representation. Okay. Now step 2 is, because in order to compute this, we have to compute the cross product of these two, and then compute the norm. Okay, so that's why we first have to compute the cross product. So the second step, we compute the cross product of these two, then compute the norm. Okay. Okay, since r is already given here, so the computation is straightforward, but the computation can be a little bit nasty. Okay. So let's compute what is partial r over partial u. So it just to do the partial derivative of each component with respect to u. So right over here is the partial first component over partial u, partial second component partial u, partial the third component over partial u. So we do that one, you do the computation is rather given by this one. Okay. Second, you can compute the partial r over partial v. You do the same thing. You do partial first term over partial v, partial second term partial v, and partial last term over partial v. Now I don't want to talk about the computation. You just give me by this. Now we have to compute the cross product. Okay, the cross product is given by, if you still remember, is a determinant of a 3x3 matrix. The first row is just I, j, and k. Okay, the second row here is whatever value you get from here. You plug in over here, and then you have last one. You put it over here. It's the last row. Okay, then you compute the the 3D 3x3 determinant. Okay, I won't talk about too much detail about the computer determinant. It's quite straightforward. You first use the first row, right? So it's I time, I don't use I1. We should have time -1 to the power 1 plus 1 because it's just 1. I ignore it as 1. So it just be, you delete the first row, first column to the determinant of this remaining 2 by 2. Okay, you reduce the order by 1. And this one is you have -1, 1 plus 2. That's why you have a negative sign. Put a negative sign here. So then you you delete the rows and column this J is on. So it's first row and the second column. So you remaining for 2 by 2 matrix. Okay, you do the determinant of that. This also have -1, 1 plus 3. So this is a positive one, so I just ignore that one. And so that's why you delete the last row, first column, first row, last column. So that's what we have. Okay, if you do the loss computation, you have, which becomes I time, this is just this guy times this guy minus this, one of these zeros, so the product will be 0. It's just this guy times this guy. It's cosine v squared times cosine u. This guy have a negative sign, right? When I do a negative sign, because this one, also this 0 times this guy is gone. It's just this guy times this guy, okay? Because this have a negative sign, and this also negative sign, so I just cancel out. So this become plus cosine v squared times sine u. Okay, that's the second term. The last one is a little bit nasty. This one is k is this guy times this guy, because this is a negative times negative, so it become positive. So we have cosine v, I put a v all together, cosine v sine v, this is sine u is sine u squared. And this minus, of course, product, right? So it becomes plus this cosine v sine v and the cosine u squared. Okay. So if we keep the first two the same, okay, there's nothing we can do further. And this one we can simplify a little bit, because if you put the cosine v, sine v, that's a common term for both terms. Then we have sine u squared plus cosine u squared. This give me 1. Okay. Then we have this guy times this guy. This is time I, this time j, this time k. So get a vector. Next step is to compute the norm of this new obtained cross product. Okay. So as I mentioned before, it's just square root of these 3 entries, square of the 3 entries. So square root of first squared, okay, the second squared, and last squared. That's what I do. Okay, if you do all the computation stuff, okay, I just ignore this one. Then you can simplify the whole stuff, and later on you just figure out this is just cosine v. Okay, so I don't talk about you can see how I compute each value, but then eventually get a cosine v. So now it comes to this point. So I already know this guy. Okay, now I have to replace this guy, right? I have to replace this one, then I can compute a double integration. Okay, so the next step is I'm going to compute this whole thing out. Okay, this one, okay, this one, okay, this is the last part. I'm going to compute this one. So here, there's a little, I want to change this a little bit. This one has to have one more term, is partial r u v over partial u cross product partial r u and v partial v and du dv. So that's what we have to compute, right? It's the same thing as, okay, as, okay, I have to have partial r u and v partial u cross product partial r u and v partial v du dv. Okay, don't forget about this term. This term very important. Okay, so what do we have to do? We just replace this x, y, z by its parametric form, which is already repeated over here. So we replace this one by x by here, y by here, and I don't care. I don't need to care about z because there's no z here in my function. Okay, so I don't care about that. So do this here. I also replace this lower bound, upper bound for. I don't use this sigma anymore. I have to use the lower bound, upper bound for u and v. So I already figured u and v here. U and v in here is given by this. Okay, given by my parametric form. Okay, if I go back over there, so I replace this one, the definition of here and here for y, x, uv, y, uv. And I'm going to replace all the lower bound, upper bound for u and v. Okay, this will keep it the same. Then I do the computation. If you do the computation, if you replace u, x, u, and v by cosine v, cosine u, and y, u, v by cosine v, sine u, Now you just do the squared, right? That's squared. The squared, squared. Don't forget this term. We have one more term. This term here. This is already computed from the previous step, right? Which is just given by cosine v. And this guy, if we do the computation, it is cosine v squared plus time cosine u squared plus sine u squared. So this is just become 1. Okay. So we end up having just integration of this guy times cosine v cubed. Okay. Then the range for u and v, for u is from 0 to 2 pi. We do this one first. For v is 0 to pi over 2. Okay. If we do this one, for the inside one, we do the inner integration first, right over here. Okay, so if you do that one, cosine v, you integrate cosine v with respect to u. So this is a constant if you consider it as a variable u over here as an integration variable. So the cosine v cubed times u, you integrate from 0 to 2 pi. Okay, and then you do that one is integrate from 0 to 2 pi over 2. So the inner integration is done. So this only remaining part is external integration. So this one integration is 2 pi times cosine v cubed, and over integration over dv from 0 to 2 pi over 2. Okay, because 2 pi is a constant, so we can pull it out. And we only remaining term is cosine v cubed. So here I do a little trick. I want to split the cosine v cubed into cosine v squared and cosine v. Okay, after doing that, I can write cosine v squared as 1 minus sine v squared, right? Because sine v squared plus cosine v squared is 1. Then I move the cosine v to the right hand side. Get a d sine v, because d sine v is cosine v times dv, right? That's the same, that's equivalent. That's why I can replace that one. So when you integrate sine v over sine 1 minus sine v squared over sine v, so I get 2 pi. So the integration of 1 over sine v is just sine v. The integration of a minus sine v squared, okay, is just 1 minus 1/3 of sine v to the cube, because the derivative of this guy will be just negative 1/3 times 3 times sine v cubed, right? So that's what comes out. I get this one, right? So that's the integration, and has to be evaluated from at pi over 2 and 0, right? So if I evaluate as pi, so I get 2 pi, still keeps the same 2 pi. So when v is pi over 2, so sine v is 1, and sine v cubed also is 1, and so it's become 1 minus 1/3. When 0 is always 0, so minus 0. As there's minus 0, it doesn't matter, right? So we can ignore that. So it becomes 2 pi times 1 minus 1/3. 1 minus 1/3 is just 2/3. Times 2 pi is 4 pi over 3. So that's my final solution for the surface integral. So let me summarize a little bit about how we do it again. So typically we first do for the surface integral, the first step is to find the parametric representation, including the functions here, x function of u and v, y function of u and v, and z function u of v, and we stack them together as my use of u of v. This gives me a vector. Also, we have to figure the lower bound, upper bound for the variables u and v. Okay, that defines the surface. After doing that, we can use this, pull this r sub u and v, this vector here, compute this partial derivatives first, then compute the cross product, and then compute the norm. So once I figure that out, somehow over here, it can be a little bit lengthy over here. The last step is we compute the integration. To compute the surface integral, what we do is we first of all rewrite this one as the double integration. By doing that, we replace the f function x, y, z, the x by x, y, z by their parametric form, which is x u sub v, y u and v. So x replaced by this, y replaced by this, z replaced by z u sub v. Of course, there's one extra term we just compute in step 2. Put over here is we do the product of that. Then we just integrate from over du and dv. That's it. And then we put the lower bound, upper bound over here. Then the remaining part just the standard double integration. Okay. Okay, so that's all for this lecture.